All right. Hello, class. Um, Hope you're doing well. Thank you to the one person, oh, now zero people. I have zero concurrent viewers. Well, I hope that maybe later on someone will view this and it'll be useful to you. Um, so, what we've got today is we've got another paper two. We're doing paper two this week. We'll do paper three next week. And then the week after that, I'll give you a little sort of mock final exam. Um, hey, Sofa. Thank you. You know what, Sofa? Thank you for watching pretty much every day. Thank you, Spicy Pepper, for both of you watching. I appreciate it. Um, so, uh, we're working on a paper two, and I'm going to do questions 1, 4, and 6. So, let's take a look here. So I'm doing question 1 first, and it says the graph shows the variation with time. Oh, by the way, this is November 2019 is the exam. So it says the graph shows variation with time of the horizontal force exerted by a tennis ball on a tennis ball by a racket. The tennis ball was stationary at the instant it was hit. The mass of the tennis ball is blah. The area under the curve is blah. Calculate the speed of the tennis ball after it leaves, as it leaves the racket. So this is a force time graph, and the area under a force time graph is change in momentum. It's called the impulse. Okay, so basically we're going to have area equals change in momentum. Now, because the ball started at rest, the initial momentum is 0. So the change in momentum is just the final momentum, mv final. Okay? So it says the area is 5.8, or the mass is 5.8 times 10 to the minus 2 kilograms. And the area under the curve is 0.84. So I can take those numbers and divide them. And we get the final velocity is about 14.5 meters per second. Okay. Show that the average force exerted by the ball on the racket is about 50 newtons. So, okay, so the notice how the peak force that the racket exerts on the ball is 150 newtons, but the average is less than that. So basically what we want to do is we want to think about this graph as if it were a rectangle with the same area. So the impulse is actually we could use the sneaky form of Newton's second law, and we could say that force is change in momentum over change in time. Now, because the force is changing, this is actually the average force. Okay, so the change in momentum was this 0.84. And then we have to figure out what was the change in time. Well, that would be sort of the width of this bell curve here. So I can see that the bell curve starts at about maybe 13 milliseconds, and it ends at maybe 27 milliseconds. 13 milliseconds to 27 milliseconds. That's about 14 milliseconds. So 14 times 10 to the minus 3. And so if we divide those two numbers, I got 60 newtons. And that's approximately 50 newtons, close enough. Okay. So there you have it. Let's continue on. Part C says, determine with reference to the work done by the average force the horizontal distance traveled by the ball when it was in contact with the racket. Work is force times displacement, okay? And the work that the racket does becomes the kinetic energy of the tennis ball. So the work is going to be 1/2 mv squared. Okay. So we know that the average force was 50. I calculated the average force of 60. However, some more people tuned in. Hey, Ben. Hey, Akshay. Hey, Christian. Hey, Jackson. Hey, Jackson, did you get my message? I messaged you on Discord regarding your comment on the homework. So just check that out. So we get 50 times displacement equals 1/2 times the mass, which was 5.8 times 10 to the minus 2, times velocity, which is 14.5 squared. And so we can solve this equation for delta x. So I got a delta x of around 0.12 meters, 12 centimeters. That seems reasonable to me. Okay. D, draw a graph to show the variation with horizontal speed of the ball while it was in contact with the racket. Numbers are not required on the axes. F equals ma. That means that force is basically the same thing as force over m is going to be change in velocity over change in time. So force is the slope of a velocity time graph, essentially. So basically what we want to do is we want to graph sort of the integral of this, if you will. And so I would graph something that kind of looks like this. Okay. So what happens is when the ball or when the racket is just beginning to make contact with the ball, the velocity is increasing slowly at first, and then once it has flexed the strings of the racket, its velocity is going to increase very rapidly, and then it starts to lose contact with the racket, and then it reaches its peak velocity. Okay. It's interesting. This kind of looks like the epidemic curve too. If you think about the coronavirus epidemic, it's the same mathematics, just applied to a different situation. All right. The next problem I'm going to do is number 4. Let me see if I have any questions. Don't. Number 4, it says a proton is moving in a region of uniform magnetic field. The magnetic field is directed into the plane of the paper. The arrow shows the velocity of the proton at 1 instant. And the dotted circle gives the path followed by the proton. Explain why the path of the proton is a circle. If you were to do the right-hand rule, if you were to put your right finger in the direction of the velocity and then your middle finger in the direction of the magnetic field, you would find that there's a force on the proton that points towards the center of the circle. So basically, the proton, it moves in a circle because the force is perpendicular to the velocity, and the force is constant. So it's a centripetal force. Something to that effect. Show that the speed of the proton, it says the speed of the proton is 2 times 10 to the 6th meters per second, and the magnetic field strength is 0.35 Tesla. Show that the radius of the path is about 6 centimeters. So in this case, the magnetic force is equal to the centripetal force. Okay. You might recall that the magnetic force, the magnitude of it is the magnitude of the charge times the speed times b times sine of theta. Okay. Because the velocity and the magnetic field are perpendicular to each other in this case, because they're perpendicular to each other, the sine theta term is going to be 90 degrees. And so for that reason, we can just get rid of the sine theta term, and you can solve for r. You get r equals mv over qb. All right. So the mass of a proton is 1.7 times 10 to the minus 27. The velocity, it says, is 2 times 10 to the 6th. The charge of a proton is 1.6 times 10 to the minus 19 coulombs, and the magnetic field is 0.35. Notice how the mass and the charge of a proton were not given. Those would be in the data booklet if you were actually taking the exam. And so I will work it out. 1.7 times 10 to the negative 27. 6. And I get oops, I goofed. Okay. So I got 0.06 meters. Actually, more like 0.061. All right. So, that was B part I. So now let's go to part II. Calculate the time for one complete revolution. We know that the velocity, if you're in a circle, is 2 pi r over the period. So that's distance divided by time. We're told that the velocity was 2 times 10 to the 6th. Solve for the period. Whoop. seconds. I like the breeze when I've got all the windows in my house open right now. I like the breeze. It's nice, but except when I'm teaching. Part C says, explain why the kinetic energy of the proton is constant. So we can say that F is, as I said earlier, the force is perpendicular to the velocity. Okay? So if we calculate the power developed by the magnetic force, we learned an equation for power. It was FV cosine theta. And force and velocity being perpendicular to each other means that the angle is 90 degrees, which means that the power developed by the magnetic force is 0. So the magnetic force isn't doing any work. And if it doesn't do any work, then that means that the speed of the proton is constant. Because if it was doing positive work, then the proton would be speeding up. So I would say something to that effect. All right. So that looks like is the second problem for today. Akshay asked the question, do protons usually move in a circle, or is that just the ideal proton in a magnetic field? Any charged particle in a magnetic field, in a constant magnetic field, is going to move in a circle. If there's no magnetic field, if there's no forces, it obviously moves in a straight line according to Newton's first law. Okay, next, so I'm doing question 6, is the last question for today. Looks like, you can see I've got a density of air and wind speed, so that tells me it's going to be a climate change, energy production kind of problem. Wind is incident on the blades of a wind turbine. The radius of the blades is 12 meters. The following data are available immediately before and after impact with the blades. Determine the maximum power that can be extracted from the wind by this turbine. So I taught you an equation for the power from a wind turbine, and I said that it was 1/2 rho A V cubed. Okay? This equation is assuming that, so this equation is assuming that the air is basically coming to a stop. Okay? Because if the air has kinetic energy after it, if the air has kinetic energy coming as it comes out of the wind turbine, then that means you haven't extracted all the kinetic energy. So this is kind of the issue with wind turbines. You can't extract all the kinetic energy from the wind, because if you did, the air would just be stopped and there wouldn't be any flow in the first place. So this is actually the power that goes in to the wind turbine. And we would use the density that goes in and the velocity that goes in. And then we can use the same equation for the power that goes out of the wind turbine. Okay? So the power that goes in is 1/2 rho, which is 1.2. The area where the blades are sweeping out a circle, so the area is going to be pi r squared, so pi times 12 squared. And then the velocity going in is 8 meters per second. Okay? For the power going out, 1/2 times the density on the backside of the wind turbine is slightly higher. The area is still the same, pi times 12 squared, and then the speed has gone down significantly. So I will compute these two numbers. So this one is 1.39 times 10 to the 5th watts. And this second one is 1.9 times 10 to the 4th watts. So the power that's extracted is going to be the power that goes in minus the power that goes out. All right, so I'm just going to subtract those two numbers. And I get, that's all I want to say about that question. So suggest why the answer to A is a maximum. Well, I would say, wind is intermittent. That's one thing. I would also say that there are inefficiencies in the generator. So you're trying to get electrical energy, and anytime you're basically, what you're doing is you have kinetic energy of the wind. Kinetic energy of the wind becomes kinetic energy of the spinning blades. And then the kinetic energy of the spinning blades becomes electrical energy, and the conversion is done by a generator. And that conversion from kinetic energy of the blade to, to electrical energy is not 100% efficient. Okay? So, I think that's it for my questions today. So, you guys are going to download this same 2019 November, and you guys are going to work out questions number 2 and questions number 6. Okay? So, hope you guys are doing well and that you have a nice afternoon. I will talk to you tomorrow.